Hi, my name is Kurt Johnson, and today I'm going to show you how to solve a time-dependent ionization balance with chloride pi. So this is going to be similar to the time-independent ionization balance or the steady-state ionization balance, which I've done a video on previously. So like before, we're going to import the standard Python libraries that we're going to need. We'll need to specify where chloride pi is located. This is where I have it. We need to append the path to where chloride pi is. And then from chloride pi, import the ionization balance. And so this is the same as for the steady state. And it gets called the same way too. We're just going to, it just has a different definition in it that will solve the time-dependent part instead of the steady state part. So like before, we need to specify the location of our SCD file for ionization and our ACD file for recombination. So these are ADF11 file formats that we're going to show here. Chloride pi can also be run from ADF04 file formats, which will be covered later. The ionization balance part can. Now what we're going to specify is we're going to specify a single temperature and a single density, because what we're going to do is we're going to solve the ionization balance at this temperature and density as a function of time. So you could specify more temperatures and more densities here, and those values would be returned as well. The way chloride pi solves the time-dependent ionization balance is through the matrix exponentiation method. So with this, it doesn't need a time step. So we can specify some non-uniform time array, which is done here. This allows us to see the fast time dynamics that happen at the beginning, and then it'll show you later at the end how it converges to steady state. So what's different here between, in addition to the time that needs to be specified, are the initial abundances. The initial abundances did not need to be specified in the steady state ionization balance, because in steady state it doesn't matter initially where the population started, it all ends up in the same steady state for a given temperature and density. This is not the case for the time-dependent ionization balance. Before steady state has been reached, the initial abundances can impact the solution. So what we're going to do here is we're going to set all the initial abundances to 0, except for the neutral atom, which we're going to give it all the population, or 100%. We're going to give it. So this is the call now to the ionization balance, which you'll notice looks very similar to the steady state ionization balance, where we give it our files. We specify this NumPy array that needs to be empty. Like before, this is a holdover from running the ionization balance from ADF04 files. We then specify the temperature grid, the density grid, tell chloride pi we're using ADF11 files, and then specify the solution time. So this is different than the steady state. We need to specify this, and then we also need to specify the initial abundances here. And once we've done that, we populate the ionization matrix just like before, and now we are going to solve the ionization balance. Instead of solve steady state, we're going to solve no source. So there is an option to also add in a constant time-dependent source term, or I guess it's not time-dependent, a constant source term into this solution, which is not covered here. Next, what's being done is plotting the time dependence at the given temperature and density. And so what I will do now is I will run this. And so it's going to take a second to run, and then I'm going to show the plot here. So this is the time-dependent ionization balance at ADV and and roughly 6.3 times 10 to the 11th per cubic centimeter electron density. So this looks similar to the steady state ionization balance, where the x-axis was a function of temperature, but now this is a function of time. And so what we can see now is we can see initially everything starts in the neutral. It then over time ionizes into the plus, which then ionizes into the 2 plus, ionizes into the 3 plus, and also the 4 plus. And you'll see after about 1.2, 1.3 seconds, these reach an equilibrium value. And so if you go back to the example I showed of steady state ionization balance, this ratio will be the same between the steady state value that would show up as that vertical line and the values reached in equilibrium here between all these charge states.